Okay, for the next portion, and this is going to go back to when we were looking at homogeneous equations, okay, especially in the determination of null spaces. And we have for what are referred to as orthogonal subspaces. And now for the backdrop, okay, to solve for least squares problems, okay, you first need to develop the concept of orthogonal subspaces. And two subspaces of Rn are orthogonal when the vectors in each subspace are orthogonal to the vectors in the other subspace. And for the definition of orthogonal subspaces, okay, so we had the subspaces S sub 1 and S sub 2 of Rn are orthogonal when the dot products between the vectors v sub 1 and v sub 2 equals 0 for all v sub 1 in S sub 1 and all v sub 2 in S sub 2. And just looking at whether the following subspaces are orthogonal. And let's say that we have S sub 1 to be equal to the span where we have in the set, okay, we had the vectors with the elements 1 and 2 as well as with the elements 0 and 1. And we'll say that we have S sub 2 is equal to the span, which consists of the vector containing the elements 2 and negative 3. And we'll say that u sub 1 is equal to 1, 2, and u sub 2 is equal to 0, 1, and v sub 1 is equal to 2 and negative 3. And if we take the dot products, okay, say between u sub 1 and v sub 1, that's going to translate to where we can take the transverse of u sub 1 and multiply v sub 1. So the transverse of what we have with 1 and 2 in column formation, that's just going to be 1, 2 in row formation, and multiplying by v sub 1, so you have 2 times 1 plus negative 3 times 2, which would be 2 plus negative 6 is equal to negative 4, and negative 4 does not equal to 0, and if the dot product does not equal to 0, then we have the outcome that the subspaces are not orthogonal. Okay, and since u sub 1 and v sub 1 do not result in a dot product equal to 0, we don't even have to test out u sub 2 and v sub 1, because if you already run into a situation where you have a non-zero dot product, you don't even have to go to the next round. And let's say that if we have S to be consisting of a couple of vectors, okay, where we have as 4 by 1 arrangements, okay, first of which we have 2, 4, 6, 8. Next we have negative 1, 2, negative 3, and negative 4. And we'll say we have the second subspace to be consisting of a couple of vectors, each also in a 4 by 1 array. And we have inside, okay, for the first vector, we have negative 3, 0, 1, 0, and the second we have negative 4, 0, 0, and 1. And looking at what we have, say, in looking at the dot products we have between u sub 1 and v sub 1, again, if I take the transverse of u sub 1, so I have 2, 4, 6, 8 across times v sub 1, and the corresponding result here is going to result where the product is equal to 0. So right now, so far, so good. And I can take the dot product now between u sub 1 and v sub 2. Again, taking the transverse of u sub 1. Again, I have 2, 4, 6, 8 across. And you have times v sub 2, negative 4, 0, 0, 1 on down. And taking the product of the corresponding parts and adding together, we also have at 0. Now, so we have the u sub 1, v sub 1, u sub 1, v sub 2, dot product combinations to amount to 0, and looking at mapping together u sub 2 and v sub 1, and I can take the transverse of u sub 2, which will be negative 1, 2, negative 3, negative 4 across, and times v sub 1, where we have negative 3, 0, 1, 0 on down, and taking the products, and so we got what's going to be 3 plus 0 plus negative 3 plus 0, and that all will add up to 0. And now just for the final part, and this is with the dot product between u sub 2 and v sub 2. And again, taking the transverse of u sub 2 and following through. And you're going to have the product. So you have negative 1 times negative 4 is positive 4. 2 times 0 is 0. Negative 3 times 0 is 0. And then we have negative 4 times 1 is negative 4. So you have 4 plus negative 4 is equal to 0. And since all the possible dot products are equal to 0, we have both of these subspaces, S sub 1 and S sub 2, to be orthogonal. Okay, now looking into what we have regarding orthogonal subspaces, we have in the mix what are referred to as orthogonal complements. And let's say that if we have that S is a subspace of Rn, well, the orthogonal complement of S is going to be the set where we have S, is going to be such that we have S, now we have along with what are regarded as orthogonal subspaces, we have in the mix what might involve the determination of orthogonal complements, and this will cross over to what we have in working with subspaces. And if S is a subspace of Rn, then we have what is referred to as the orthogonal complement of S, where we have the orthogonal complement is going to be a set, where we have the vectors to be elements of Rn, and where the dot products of what we have for all the vectors, v and u, to be equal to 0, and where we can have, again, u is an element of Rn, and we have the vector v to be an element of the subspace S. And we have the orthogonal complement of the trivial subspace 0 is going to be all of Rn, and conversely, the orthogonal complement of Rn is going to be the trivial subspace 0. And let's say that in looking for orthogonal complements and finding what are referred to as direct sums between the subspaces and their orthogonal complements. Let's say that first of all we have S to be the span of what we have with the vector consisting of 2 and negative 3. And now for what we have in this case, right, so we have A is going to be the coefficient matrix, which we had to be at 2 and negative 3. And we have with the vector u, we have x of 1 and x of 2. Now looking for the null space, we're going to be looking at taking the product of the transverse of A and the vector u with x of 1 and x of 2 to be equal to 0, and just arranging things here. So we have the transverse of A with 2 and negative 3 times the vector u with x of 1 and x of 2 equal to 0, and writing or expressing as an augmented matrix. So you have 2, negative 3, 0, and putting in reduced row echelon form. So we're going to have 1, negative 3 halves, and 0. And so we'll have x of 1 is going to be equal to 3 halves of x of 2, since x of 1 minus 3 halves of x of 2 is equal to 0. So we have this equation, and x of 2 is going to be a free variable, and we're just going to set this equal to t. And if x of 2 is equal to t, well, x of 1 is equal to 3 halves of t. And looking for what we have for the null space. So u consisting of x of 1 and x of 2, and both of these are variable terms in the letter t, and so we have 3 halves of t, and so for u, the null space, we have t times the vector where we have 3 halves and 1. So just factored out the t. So the basis for the null space is going to be the vector with 3 halves and 1. And so the orthogonal complement of the subspace S is just going to be the span consisting of the vector 3 halves and 1. So you have like any multiple of 3 halves and 1. And so for the subspace, the span which we had of 2 and negative 3, and the complement of S, which is going to be the span of 3 halves and 1. So any multiple we're going to have throughout between these subspaces, and as well as the complements, that's going to be all of R2. So we have for the direct sum of S and the orthogonal complement, that's going to come out to R2. Now let's say that we have S to be the span where we have consisting of 1, 2, 0 and 0, 1, 0, and we're looking for the orthogonal complement. So again, just looking for the null space concerned. Now we got A, the coefficient matrix, consisting of 1, 0, 2, 1, 0, 0, and for U we have x of 1, x of 2, and x of 3. And the transverse of A, we have the top row with 1, 2, 0, bottom row with 0, 1, 0. And again, we're looking for the null space U. And so we're looking at the values of x of 1, x of 2, and x of 3, where we're going to have U to be such that the product between that and the transverse of A is equal to 0. So expressing what we have in the setup in augmented matrix terms. Okay, so you have 1, 2, 0, 0 across, 0, 1, 0, 0 also running across, and putting in reduced row echelon form terms. Okay, so we'll have 1, 0, 0, 0 across, 0, 1, 0, 0 also running across. And from the top row, we have automatically the x of 1 is equal to 0. Bottom row, we have signaling that x of 2 is equal to 0. But guess what? There's nothing where we have x of 3 isolated. Okay, and so x of 3 is going to be a free variable. And we're going to set this equal to t. So for the null space U, okay, you're going to have, filling in for x of 1, x of 2, and x of 3, you're going to have the vector consisting of 0, 0, and t. And factoring out the variable t, so we're going to come out to 0, 0, and 1. And the basis for that null space is going to be the set consisting of the vector containing 0, 0, and 1. And for the orthogonal subspace, okay, that is going to be the span of that particular basis. So the basis for the null space or the orthogonal complement, again, that is 0, 0, 1, and the orthogonal complement is going to be the span of 0, 0, and 1. So what I mean by span is that you're looking at any multiple of 0, 0, and 1, like 0, 0, negative 22 or 0, 0, 57. That would be part of the set. And once again, for the direct sum of the subspace and the orthogonal complement, okay, that is going to be all of R3. Now, let's say that we have S to consist of what we have in the span, say 1, 2, 0, 0, 1, 0, 0, 0, 1. And again, the coefficient matrix we have with 1, 0, 0, 2, 1, 0, 0, 0, 1. And taking the transverse, okay, so I have 1, 2, 0, 0, 1, 0, 0, 0, 1. And for the null space U, which we're going to try to determine, we have, again, consisting of x of 1, x of 2, and x of 3. And setting up stuff that we have in line with the transverse of A times U is equal to 0, and converting to what we have as an augmented matrix. So you have 1, 2, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and putting in terms of the reduced row echelon form. So we're going to have 1, 0, 0, 0, 0, 1, 0, 0, and 0, 0, 1, and 0. And so we're going to have for U, okay, it's going to turn out that all of the elements x of 1, x of 2, and x of 3 will be equal to 0. And since the null space of what would otherwise be the orthogonal complement is 0, it's going to have no basis whatsoever. So in effect, the orthogonal complement has no basis, and the sum between the subspace and what would have been the orthogonal complement, okay, that is not even applicable. Now, let's say that if we have S to consist of also three 3x1 vectors, okay, now what we had before, we had three 3x1 vectors, but again, there was no basis from which we could determine the orthogonal complement or the direct sum that follows. But now with the elements, so we got 1, 7, 8, 1, 7, 9, 1, 7, 10. And again, we had the coefficient matrix where we have 1, 1, 1, 7, 7, 7, 8, 9, 10 as we go row by row. And the transverse, also going row by row, we have 1, 7, 8, 1, 7, 9, 1, 7, 10. And we have for U, the null space, we have x of 1, x of 2, and x of 3. And setting things up and solving for U. Okay, so we got the transverse of A times U is equal to 0. So we got the setup and expressing in augmented matrix terms. So we have 1780, 1790, 1710, 0. And the reduced row echelon form is going to become 1700 for the first row. Next row we have 0010. Last row we have zeros running across. And so we have a consistent system. And taking what we have from the top row, we have x of 1 plus 7x of 2 is equal to 0. So you have that x of 1 is equal to negative 7x sub 2. And from the second row, we had the x of 3 is equal to 0, and there's nothing among the rows that will have x sub 2 isolated. And so we have, with x of 2 is a free variable, we have the x of 2 is equal to t. And so that means that x of 1 is going to be equal to negative 7 times t. So for the null space, we have u is equal to the 3 by 1 matrix consisting of negative 7t, t, and 0. And factoring out the t, we have t times. And we have the vector with negative 7, 1, and 0. And the vector with these constants, that is going to be the basis for the null space, or the orthogonal complement, which would be the set consisting of, again, the 3 by 1 vector with negative 7, 1, and 0. So the orthogonal complement is going to be the entire span of the basis. So you had the span, again, consisting of the set negative 7, 1, and 0. And we're going to have throughout that the subspace and its orthogonal complement will have a direct sum that will amount to R3. Now, let's say that if we have a couple of what we have in the case of 4 by 1 vectors, and we have a couple of these. Okay, so you have first vector we have with 1, 2, 1, 0. Next we have 0, 0, 0, 1. And if I take the transverse of A, so you have 1, 2, 1, 0 for the top row, 0, 0, 0, 1 for the bottom row. And we have for the null space, okay, we have the vector consisting of x of 1, x of 2, x of 3, x of 4. And running it through the process, again, where we have the transverse of A times U is equal to 0. And guess what? Putting in augmented matrix terms. And this is already going to be in reduced form. So you have 1, 2, 1, 0, 0, 0, 0, 1, 0, or 0, 0, 0, 1, 0. And so we're going to have for x of 1, that's going to be equal to negative 2x of 2 minus x of 3. X of 4 is equal to 0. And so we're going to have the x of 2 and x of 3 will be free variables. And so we'll have for x of 3, that is equal to t. X of 2 is equal to s. And back substituting, we have that, or substituting, x of 1 is equal to negative 2s minus t. So the null space u, okay, we're going to have equal to negative 2s minus t. And for x of 2, we have s. X of 3, we have t. X of 4, we already have baked in, is equal to 0. And then partitioning and separating the s and the t terms. Okay, so we have s times the 4 by 1 vector, where we have from x of 1, we have negative 2. And from x of 2, which is already s, we have s times 1. X of 3 and x of 4 don't have any s capacity, so we have zeros to follow. And then we have plus t. And since x of 1 consists of negative t, we have t times negative 1. And again, x sub 2 does not have any t present, so that's going to be 0. And x of 3 is 1t, so we have t times 1. And again, x sub 4 is already at 0. And so for the basis for the null space or the orthogonal complement, this will be the set consisting of negative 2, 1, 0, 0, as well as negative 1, 0, 1, and 0. And so the orthogonal complement is going to be the entire span of what we have for this null space basis. And so we have for the direct sum between the subspace and this newly formed orthogonal complement, this is going to be R4. Now, let's say that if we had the S is going to be the span of 0, where we have this in the form of 3 by 1 arrangement, whereupon we have 0, 0, and 0. So the coefficient matrix, again, will be 0, 0, and 0 vertically. And for the null space, we have x of 1, x of 2, and x of 3. And the transverse, we have zeros running across. And so we have this 1 by 3 arrangement. And looking at what we have, again, with the transverse of A times U equal to 0, with U being the null space. Okay, and putting in augmented matrix terms. Okay, so we have nothing but zeros running across. Okay, and so we don't have x of 1, x of 2, or x of 3 itemized. All of these will be technically free variables. And so we'll say that we have x of 3 is equal to t, x of 2 is equal to s, and x of 1 is equal to r. And so the null space, again, we have r, s, and t, and then partitioning out. So you have R times 1, 0, 0, and you have plus S. And since S is only in the middle, we're going to have S times 0, 1, 0, and with T coming last. And at the bottom, we have T times 0, 0, and 1. And the basis for the null space or the orthogonal complement is going to be the set consisting of 1, 0, 0, 0, 1, 0, and 0, 0, 1. And so the orthogonal complement is going to be the span over the set of these three vectors, and we're going to have in effect that the direct sum between S and its orthogonal complement will be all of R3.